Albert Einstein is often regarded as one of the greatest geniuses in human history, especially for his profound contributions to physics and science in general. He is particularly famous not just for the theory of relativity, but for his two theories of relativity, both of which were developed in the early 20th century. The first is the theory of special relativity, which describes the motion of objects and electromagnetic fields. Remember, light is an electromagnetic field in the absence of gravitational fields. Special relativity introduced two revolutionary concepts that were quite groundbreaking for physicists at the time. The first is that the speed of light is constant for all observers, no matter how fast they're moving. This means that even if you're traveling close to the speed of light, you would still see light moving at its usual speed relative to you, a strange and fascinating aspect of our universe. The second concept is that the laws of physics remain consistent, regardless of whether you're in a fast-moving rocket or standing still at a supermarket. According to Einstein himself, special relativity was a good idea, but not necessarily a genius one. He believed that if he hadn't developed it, someone else eventually would have, as the key concepts were already being discussed by other physicists who were close to reaching similar conclusions. However, Einstein's humility doesn't fully acknowledge the brilliance of the theory, in my view. The same cannot be said for his general theory of relativity, which describes how objects and electromagnetic fields move in the presence of gravity. Unlike special relativity, which was more of a logical extension of existing ideas, general relativity was a true leap of genius. At the time, there was little scientific evidence suggesting the need for a new theory of gravitation. Newton's theory of gravity was considered sufficient, but Einstein's development of general relativity fundamentally changed our understanding of the universe. It's hard to imagine anyone else in the early 20th century coming up with such a revolutionary idea, if not someone as brilliant as Albert Einstein. In this video, I'll explain the concepts behind general relativity, or as some might call it, the happiest thought of his life. Einstein himself referred to it as such, marking it as a turning point in his thinking. But before we dive into general relativity and gravitation, it's important to revisit an idea from special relativity, which historically came first. Special relativity introduced the notion that space and time are not two separate entities but are intertwined, fundamentally changing how we perceive the fabric of the universe. In a more fundamental sense, space and time are like two different directions within the four dimensions of space-time. This means we have 3 dimensions of space and 1 dimension of time, giving us a total of 4 dimensions. The most significant consequence of this is that when you change your movement through space, you also change your movement through time. The faster you move, the slower time passes for you compared to someone who remains stationary. This is why astronauts who have spent time traveling quickly around Earth are slightly younger than they would be otherwise. But don't worry too much, this difference is incredibly small. With this in mind, let's dive into the goal of general relativity. To describe how matter moves in the presence of gravitational fields and how matter itself generates gravity. To appreciate why Einstein's reasoning was so brilliant, we need to clarify 2 things. What exactly is motion and what exactly is gravity? And trust me, this is going to be more interesting than your high school geometry class. It'll involve water slides and cats. Seriously, I promise. Let's start with motion. The definition is straightforward. In physics, the study of motion is the study of how an object's position changes over time. To figure out how an object moves, we need to know the force acting on it. Once we know the forces, we can determine its acceleration using the formula force equals mass times acceleration. Once we have the acceleration, it's easy to determine how an object will move. So to summarize, understanding motion is all about understanding acceleration. Keep that stored in your brain's hard drive, it's crucial. On the other hand, in classical physics, gravity is understood as a force that depends on the mass of the objects involved and the distance between them. To calculate the gravitational force, you simply use F equals ma to determine the acceleration, and thus the movement of the objects involved. The key idea here is that gravity is the effect that matter has on other matter at a distance. However, Einstein wasn't satisfied with thinking of gravity purely as a force. He believed there was a better way to understand the connection between gravity and the motion of objects. As we've just discussed, to determine motion, all we need is acceleration. So the challenge was to figure out how gravity causes acceleration, and it was a mental experiment that led Einstein to what he called the happiest thought of his life. Imagine you're standing in an elevator on top of a scale. Just to be clear, you're the one on the scale, not the elevator. When the elevator is stationary, you feel your normal weight, and the scale shows your usual weight. Now, when the elevator starts moving upward, you'll feel slightly heavier, and the number on a scale will increase a bit. Conversely, if the elevator begins to descend, you'll feel a bit lighter, and the scale will show a lower value. But now, let's take this scenario to an extreme. Imagine the elevator cable breaks, and you start to plummet. In this situation, you wouldn't feel your weight anymore. You would be in free fall. The scale, too, would register nothing as it floats alongside you. In this scenario, you're floating while accelerating in a gravitational field, which is essentially equivalent to floating in a vacuum of space. In space, you wouldn't feel your weight either, but there's no gravity or acceleration to speak of. During free fall, you're accelerating due to gravity, yet you float. In a vacuum of space, you float without any gravity or acceleration. The connection between falling inside an elevator and floating in space is so profound that if your elevator had no windows and you were in free fall, you wouldn't be able to tell whether you were falling or just floating in an elevator in the middle of space. This reveals a deep relationship between these two concepts. Now, imagine one final scenario. You're in a spaceship accelerating at 9.8 meters per second squared. The same acceleration as Earth's gravitational field. If you step on a scale in this spaceship, you would show the exact same weight as if you were standing on Earth. In other words, accelerating in a spaceship feels just like being in a gravitational field. Accelerating is like gravity. And here's Einstein's happiest thought. Gravity is simply acceleration, with no forces involved. At every point in space-time affected by gravity, it's as if there is a sign indicating the acceleration a body should have at that point. Gravity acts as a map that shows how objects should accelerate when they're near planets, stars, and other massive bodies. But how can something accelerate if there are no forces involved? There's one thing in physics that can alter the motion of an object without directly relying on forces: geometry. And here's where the cats come in, as promised. Let's start with a simple example. Imagine you want to drop a cat from a height of 20 meters, and you have two options. You could either let it fall freely, where it would unfortunately hit the ground, or you could send it down a water slide into a refreshing pool. From the perspective of the forces involved, both scenarios are essentially the same. It's just gravity pulling the cat, but in the second case, the geometry of the situation is different. There's a water slide guiding the fall in a specific way. What determines the difference between these two falls isn't the force of gravity, but the curves of the slide. In other words, the fall is dictated by the geometry of the slide. Geometry then can influence motion, or put another way, geometry can cause a gravitational acceleration. In summary, gravity is simply the water slide for all matter. All the planets, stars, and galaxies are like giant cats sliding along. If anyone asks if I said that, I'll deny it. But in more technical terms, gravity is the geometry of space-time that guides the acceleration of objects. Often, we say that gravity is the curvature of space-time, which is basically the same. When an asteroid moves through space-time, it moves according to the curvature of space, which we call gravity. Similarly, when a train moves, it simply accelerates in a straight line, and the path it takes is determined by the curves or the geometry of the train tracks. But gravity is generated by matter, so when a massive object like a star is present, it curves space-time around it. The classic example of this is imagining a stretched out sheet. If you roll a marble across the sheet, it moves in a straight line. Now, if you place a heavy bowling ball in the middle of the sheet, The sheet curves significantly, much like space-time curves in the presence of a star. If you roll the marble again, its path will be altered by the curvature of the sheet caused by the larger ball. In the same way, an asteroid's path is altered by the curvature of space, just as the marble's path is altered by the curve in a sheet. At no point does the asteroid need to be aware of the space-time curvature. It simply tries to move in a straight line and ends up following the curve of space-time itself. According to general relativity, Earth is simply trying to move in a straight line, but the curvature of space keeps it locked in orbit around the Sun. The same principle applies to light. Light always tries to travel in a straight line, but it follows the curvature of space-time as well. In essence, what general relativity tells us is that matter dictates how space should curve, and the curvature of space tells matter how to move. That's the key insight. You don't need force to describe gravity. It's far more natural to describe it as the very geometry of space-time, the curves of the universe itself. General relativity also leads to various predictions that have been confirmed through experiments, like the bending of starlight near the Sun. And to clarify, the stars themselves aren't close to the Sun, it's just the light that appears close. It also accurately predicts the orbit of Mercury, something Newtonian physics couldn't do. General relativity even introduced the concepts of black holes and wormholes. But the true beauty of the theory lies in how it forces us to see the universe in ways we never imagined. It's like taking our doll, boxing brains, and making them look at everything from outside that box. For me, there's nothing more wonderful than that.